So integrating functions in the form of f bracket ax plus b. So if we know the integral of a function, we can integrate a function of the form of f ax plus b using the reverse of chain rule for differentiation. And this is based on the understanding that integration is the inverse of differentiation. So if we know a function and what it differentiates to, then the answer that we have for that function, if we integrate it, we should get back to the same thing. So there are a lot of integrals that we can complete by understanding the chain rule, which we normally use to composite functions. Remember, where we have an inner function and an outer function, or a function within a function. And if we know how to differentiate using the chain rule, which is what this is based on, then we should know the integral of functions which are in that form. So as you can see here, that these functions are composite functions, where you've got a function within a function. Okay, all of these are functions within a function, composite functions. So how do we tackle such integrals? Well, let's first of all understand by looking at A, what function would have differentiated to give us cos of 2x plus 3? Well, suppose we started off, we know that something to get to cos by differentiating, we would have started off with sine, because sine differentiates to cos. So ideally, we would have say let y, so letting something equals to something is a nice way of doing this integration by considering the reverse of chain rule. So we're going to say let y is equal to sine of that same 2x plus 3. So if we started off with y equals sine of 2x plus 3, why did I start off with sine? Because I know the differentiation of sine gets us to cos. So if I then differentiated this function here, then what would I have got? Well, if I differentiate this using the chain rule, we get, well, differentiation of sine is cos of the same angle. And remember, we then multiply by the differentiation of the inner function being 2x plus 3. So the differentiation of that, as we can see, is 2. So we would multiply by 2. So we can see here that differentiating this function y equals sine of 2x plus 3 gets us to that. So therefore, what is the integral of the function that they're asking for here, which is cos of 2x plus 3? Well, we can see here we don't quite have cos of 2x plus 3. What we have is cos of 2x plus 3 times 2. I'll just put the times 2 here at the beginning instead of there. I'll just write it here, times 2, and get rid of that. So that differentiates to give us that. Now, can we then do something to it? Well, we can adjust both of these. Suppose I wanted to get to this function here, which doesn't have the times 2, then what I would need to do is I would need to divide both of those functions by 2. So if I divide this by 2, I'd need to divide the y by 2 as well, because then that would give me exactly the same. Division by 2 doesn't affect a differentiation, because all that is division by a number. It simply means you are just scaling it down. Okay, so scaling it by a half. And that's absolutely fine. So then what that's telling us is that actually, if we were to differentiate y is equal to half sine 2x plus 3, the answer that we would have got to would have been cos of 2x plus 3. Okay, and that's because the half times 2 gets us 1. So I adjusted it by that factor of a half. So the differentiation of this gets us this. Okay, so if we differentiate to get to this, and this we can see here, what we get to is exactly the same as what we were trying to integrate. Then we know that since differentiation is the reverse of integration, then surely if we integrate this, we should get back to that. Okay, so then the question was, what is the integral of cos 2x plus 3? Well, we can go and say the integral of cos of 2x plus 3 dx is equal to a half sine 2x plus 3. And that we did by considering the reverse of chain rule. Okay, so this is the process of integrating by reverse of the chain rule. So remember, we introduced what y was, and how did we decide on that? Well, we thought about what function would have differentiated to get us the cos. It would have been sine of something, and we started off, and then we had to adjust it by a factor, the factor being a half there, okay, and we multiplied both the y and the dy by dx by half to make cos 2x plus 3, which is exactly what we were trying to integrate. Okay, so let's take a look at the second example here. So integrate e to the power of 4x plus 1. So this is the function that we want to get to. Now, start by writing down what function would have differentiated to get us this. So we are considering the reverse of differentiation. So we'll say here, let y equal to a function that would have differentiated to that e to the 4x plus 1. Well, that function would still have to be e to the 4x plus 1, because remember, whenever we differentiate exponential function, we get the same thing but multiplied by the kind of coefficient. Okay, so suppose y was equal to e to the 4x plus 1. We don't need to know if there was a number in front. We can adjust that later. So let's go and differentiate this using the chain rule. So using the chain rule, when we differentiate this, it becomes e to the 4x plus 1. And chain rule is applied compositely. So we've got the function here, 4x plus 1, which is the inner function. So we then times it by the differentiation of 4x plus 1. So the differentiation of 4x plus 1 is 4. So we would then times it by 4. So that's what we get when we differentiate y. We get dy by dx is equal to 4 lots of e to the 4x plus 1. Now let's take a look at what we're trying to get to, what we're trying to integrate. What we are trying to integrate just has e to the 4x plus 1, whereas here we've got 4 lots of e to the 4x plus 1. So what we want to do is we want to adjust this. What's our adjustment factor here? Well, if we times everything by a quarter, then what we end up here with is e to the 4x plus 1 is what dy by dx is. So since we differentiated from there to get to this, okay, so that's differentiating, then surely if we integrate this, we get back to that. So now we can see that what we are actually integrating, the e to the 4x plus 1, if we integrate that, the answer should then be 1 over 4 e to the 4x plus 1. So we can then go and say that e to the 4x plus 1 integrated with respect to dx will actually equal to 1 over 4 e to the 4x plus 1 plus c. So the third example here, part C, it says we're trying to integrate sec squared 3x dx. So here we need to first of all start by considering what would have differentiated to get us sec squared 3x. So this requires a bit of knowledge. So we probably have to go to our formula book, because I mean, sec squared 3x, getting that differential is not something that we know from the top of our heads. So go to the formula book, look at the differentiation section. What differentiates to get us sec squared? And if you look at your formula book, there is one of the results, and that result here, what differentiates to get sec squared? It's tan. Okay, tan of x, or tan of 3x differentiates to get you sec squared 3x with a coefficient in front of it. Okay, I'll just remind you of that. It's written in our formula book as sec kx, written as f of x, and in the f, when we differentiate that, oh sorry, wrote it the wrong way around, tan kx, and when we differentiate that, we get k sec squared kx. So we can see here what differentiates to get us sec squared kx, tan kx. So what's our starting point? We say let y equals to tan kx, because that differentiates to get us that. Or part way, be it adjusted by a factor. We don't need to know what that factor is yet. We'll deal with that later. So let's go and differentiate this tan kx then. So if we differentiate tan kx using our standard result given to us in the formula book, then that then gives us k sec squared kx. Now, obviously, we know what the value is. We're not using kx, we're using 3x here. So I'll replace that with 3x, and then that becomes 3. So I know that differentiation of tan 3x gets me 3 sec squared 3x. Now, we are trying to get our differentiated answer to become sec squared 3x. What I have here is 3 sec squared 3x. So I'm going to adjust it by multiplying it by a third, and I'm going to multiply by a third there as well. Whatever I do on the dy by dx, I have to do the same factor that I'm going to multiply by on the y as well. That then simplifies, giving us sec squared 3x, which is exactly what we're trying to get to. That matches what we're trying to integrate. So since the differentiation of that gets us this, differentiating, then we know integrating this will get us to that. So then we can go and answer the question, which is the integral of sec squared 3x with respect to x is equal to a third tan 3x plus c. So we need to consider, first of all, for part A, what would have differentiated to get us that? Now, let me write this out slightly differently so you might actually recognize it. So we're trying to get to this form here. That's essentially what that is, 1 over 3x plus 2 dx. I know it's got the dx on the numerator, but it's better to write it in this form. Now, this, as you can see, is a reciprocal. It's in the form of 1 over x, right? So we need to understand how we get to this answer. And remember, we get 1 over x, or this particular form, when we differentiate a particular type of function, and that function that we need to consider is ln of x, which we looked at as the standard results. So we will say let y equal to ln of 3x plus 2. Okay, and we'll consider differentiating ln function using chain rule, which we've looked at before. So how do we differentiate this? Well, dy by dx, if we differentiate this using the chain rule, it becomes 1 over 3x plus 2, okay, times by the differentiation of that inner function, times by the differentiation of that is 3, so times by 3. Now, we can see here that what we need to get to is 1 over 3x plus 2. Now we've got this extra 3, so we need to then adjust this by a scale factor. So we're going to times it by 1 over 3, because then that 3 will cancel with that, leaving us with 1 over 3x plus 2, which is what we want to get to. Okay, so differentiating this gets us this by chain rule. And so the reverse of differentiation, integration, will get us to the answer that we're looking for. Remember, this 1 over 3x plus 2 matches that, so then we can go and say that the integral of 1 over 3x plus 2 dx is therefore equal to a third ln of 3x plus 2 plus c. So we're now considering part B here, integral of 2x plus 3 to the power of 4. So the first thing we need to ask ourselves is what would have differentiated to get us this? Now this is obviously using the chain rule. So let's start by writing let y equals 2. It would have been 2x plus 3, but I'm going to increase that power of 4 to 5, because when I differentiate this using chain rule, when I differentiate this y function using chain rule, I would reduce that power from 5 to 4 to get to that. So I asked myself, what would have differentiated? And if I see something that has a bracket with a power on it, I would then increase the power, because when I differentiate this, I would need to reduce the power to get to that. So let's see what I'm referring to here. If we apply the chain rule and differentiate this, well, when we differentiate this, remember, it becomes the power, we times by the power, keep the inner function as it is, the 2x plus 3, reduce the power of the 5 becomes 4, and then times by the differentiation of the inner function. So differentiation of the inner function is 2. And so then we can see here this simplifies to 10 lots of 2x plus 3 to the power of 4. Now notice what we're trying to get to. We're trying to get to 2x plus 3 to the power of 4. So there's an extra 10 it's been multiplied by. So here I'm going to apply a factor that I'm going to times both functions by in order to then get to what I want. So I'm going to times it by a factor of 1 over 10. And then that simply gets us to 2x plus 3 to the power of 4, which is exactly what I was trying to integrate at the beginning. Okay, so then I can say, well, if this differentiates to this by chain rule, to this, then this would integrate to that. So what is the integral of that? Integral of 2x plus 3 to the power of 4 is equal to, oops, sorry, wrong one. Is equal to 1 over 10 2x plus 3 to the power of 5 plus c.